All right, so a quick recap. Four industrial revolutions, right? So the first industrial revolution really started in about the 1770s, and it allowed us going from using our hands to using steam and water-powered machines. Then about 100 years later, introduced electricity. That led to the second industrial revolution, which gave us automation and mass production. And then about another 100 years later, computers arrived around the 1970s. And this allowed us to automate some of the blue collar work in factories with computerized machines. And then the fourth industrial revolution really has just started. Thanks to the development and democratization of high-speed communication. We're no longer looking at individual computerized machines, but a whole connected network of them. And we have intelligent factories, and some of the underlying technologies of this new industrial revolution is really the Internet of Things. We now have smart machines that have sensors in them that are connected to networks and talk to each other and alert someone if something is going wrong within the machines. These intelligent connected machines are generating huge volumes of data. And we can now employ systems and software such as artificial intelligence to make sense of that data. We can get things like predictive maintenance, where a machine can tell you if something is about to go wrong just before it's about to go wrong. And we have interconnected supply chains where ships are talking to warehouses, they're talking to trucks. It also enables us to have more intelligent robots and autonomous vehicles and drones. So this means that we can now have ships arriving, the containers can be tracked, the warehouses can be ready, even if there's a delay. And we can now ship things automatically using delivery robots. So this, in essence, is Industry 4.0. It's a new world of smart connected machines and intelligent robots. It really requires us to rethink our business and to take our business from the third industrial revolution, into this brave new world of Industry 4.0. And we need to develop our skills, and we need to figure out what roles people will play in all this. We're now talking about cobots and co-sharing our work environments with these intelligent robots. So we need to make sure we prepare for this new industrial revolution so we can really leverage the technology. And just like every previous industrial revolution, the organizations don't really prepare for this adoption, will very quickly be left behind. One of the biggest, I'm listing four of the key main benefits there of Industry 4.0. It's just tremendous improvement in productivity, improvement in efficiencies, better flexibility and agility for your company, and overall increased profitability. So the first subject that I really want to get into is model-based definition. And there is a lot to this. There's a lot of different manufacturing disciplines. I'm going to particularly focus on CNC manufacturing, only because out of all the other manufacturing disciplines, it's going to give you a good idea of the different capabilities that softwares have that can actually consume digital data. So typically, as a supplier company, you may receive a technical data package, a package of information that you need to quote on a part. That will typically be 2D drawings, other requirements, specifications, and then if your customer sends it to you, a CAD model as well. So these would be the three items that you see up there in the flowchart. And that's what we call a technical data package. And normally you would, your individual disciplines within your manufacturing, if you do any kind of analysis on the information that you're giving, obviously costing, you have to quote the part out, you have to come up with a manufacturing process, your production, and then quality control. All of these different disciplines will use that data individually to come up with their processes. But the way in which it's done right now is, as an example, if I'm in manufacturing engineering, I'm going to take a look at the 2D blueprints, and depending on the dimension of the feature, depending on the tolerance that that feature has to be made to, and any other specifications, I'm going to have to make conscious decisions on what machine to use, what tooling to use, what tool pathing to use in order to produce that feature to spec, right? And similarly for production, quality control, costing, they would go through their manual processes of coming up with their numbers. The benefit of model-based definition is that you have all of this data in a digital format. And when you have information in a digital format, it becomes machine consumable. And what that means is taking all the PMI, the 2D drawing, all of your geometric dimensions and tolerancing, and putting it onto the 3D CAD model. So each feature has attached to it, excuse me, inherently it has the dimensions from the 3D geometry, and then attached to that geometry, you have all of the requirements that your customer is putting on there in order to accept that feature to be in tolerance. When I say digital consumption, I want to go through specific examples to kind of give you more of an idea of what that means. So we're going to talk about particularly manufacturing engineering and quality control. So here on the screen, I'm showing a screenshot of a particular software. In this case, it's SolidWorks, and then their particular CAM solution called CAMWorks. But it's other software also have similar type capabilities. I'm just showing one as an example here. On the right, you see a part that has PMI on it. That is all the dimensions that are attached to particular features. They have their individual tolerance ranges. And what you can do in CAMWorks, particularly, it has a function or a capability called tolerance-based machining. So it's one step further than feature-based machining, where a CAM software will recognize machinable features, and then you can then develop tool paths for those particular machinable features. With tolerance-based machining, you can actually teach the software the decisions you would make based on the tolerances that are attached to each one of those features. So for example, if I had a hole of, let's say, 2000s, plus or minus 2000s tolerance range, right? I'd probably just choose a spot drill operation followed by drilling operations. That's typically sufficient to produce that hole. If I had a hole tolerance of, -0 plus 5 10,000ths, I'd probably want to do a spot drill, then a drilling operation that's slightly undersized, and then a reaming operation to really get it to that tolerance range. So I'm making that conscious decision. But here, I can actually teach my software to do the same. So I can set up what SolidWorks, CAMWorks will do is it'll give you a list of all of the recognizable machinable features. And then for each one of those features, you can actually set up a tolerance range. And then for that tolerance range, you can set up the strategy that you would use to produce that particular part given that tolerance. So you're, in essence, teaching the software what you would normally do. And once you have that information taught to the software, now that data that you have in a digital format is very, very valuable, because it becomes a push button operation where you can have a NC program generated. And we'll go into a little bit more on that in the case study. As an example, the 3 divot, like the spherical cuts that you see on the top of the part there, they're colorized differently. And what the CAMWorks did was each one of these has a different surface finish wall. That's why they're highlighted. This particular feature has I think it's a 16 RA, and this one I think is a 64. So you can see, it's probably hard to see here, but the SolidWorks CAM, what it did was it automatically selected the right step over to achieve that surface finish. As I said, I'm showing SolidWorks particularly here just so that we can focus and concentrate on one, so I can give you the details. But generically speaking, NX CAM has this capability. CATIA and ProE also have similar capabilities. Mastercam is coming out with tolerance-based machining. So by no means am I, this is the kind of techniques that the software companies are building into their softwares to give you the ability to teach what you typically would do manually. This is an example of an inspection workflow, right? It's a collection of different software, if you will, a software tool chain that reuses that single model, that model-based definition throughout all of the different processes. So here, yeah. Okay, okay, yeah, no problem. So on the left here, the OEM is using PTC Creo to author a model, right, to author a design. And in this case, PTC Creo does not have the ability to output one of the two generic formats, which for inspection is going to be the QIF format. So inherently inside a CAD software, when you create a part file or an assembly file, you can add PMI to it. That's been in existence for a long time. What's now becoming, what makes that more powerful now is the consumption of that data and the ability to teach your manufacturing software what you can do with that data, right? So now we're calling this entire process that works model-based definition. And there are two generic kind of shareable formats that are non-CAD specific. One is the STEP AP242 format, which is more friendly to manufacturing processes. And then you have the QIF format, which is more friendly to inspection processes. Now, QIF is a more mature file format, so it actually works more repeatably. But an OEM that produces a model in PTC Creo wouldn't have the capability of exporting QIF. It just doesn't have that built-in function. So what we're using here is a software from MBD Vidya we're using a product from CAP Vidya called MBD Vidya, which is a standalone software, but it also puts a plugin to your CAD software to enable you to export out QIF. So what you're seeing in the workflow here is a model being authored in PTC Creo, using the plugin to export that Creo model to a QIF file. So the QIF will contain the 3D geometry as well as all of the PMI. And then now that I have that file, I can consume that in my inspection process. So the next softwares that you see in the tool chain here are the softwares that the supplier company would use. So you can take that QIF file, you can put it into Origin Checkmate software, which is a software that runs within SolidWorks that can use MBD data to automate CMM programming. It completely eliminates the need for you to go in and manually tell the system where to program, via positions or safe positions, things like that. It will look at your datums. It'll do the alignment on its own. It'll read the requirements and come up with a probing path that is appropriate so that you can get the right data out. And what I can do from there, once I have the CMM program produced, I can put that into a piece of software called MetroSage or Pundit CMM, and that can optimize my CMM path, right? So you can reduce your cycle time. It does a lot in that particular software. And then you can, once you run your CMM, you can export that data out into the CAP Vidya MBD software to visualize it, to see a color map or a heat map of where that part is in tolerance, out of tolerance. And then that particular software also has a link to the Pratt & Whitney portal, so you can supply that data back particularly to Pratt. So this is an example of many different softwares using model-based definition. You're not recreating anything. You're not importing a CAD model and then setting up your requirements for each of the features. You're not telling it that this particular feature has a perpendicularity requirement, or this one has cylindricity, or there's a flatness. This particular feature has a plus or minus tolerance of whatever. It's reading all that information, so it sets everything up for you automatically. It saves a ton of time. This is another example if you're using non-contact inspection like laser scanning or structured light. On the left, you see the SOLIDWORKS interface with a model and PMI on it. And in this case, we're just directly importing that native SOLIDWORKS file into a piece of software called GeoMagic Control X. It can read the SOLIDWORKS file with the PMI, and everything's set up. There's nothing further to do other than to scan the actual part that was produced, import that scan, and then GeoMagic will go through and align it to the datums and output the inspection report. Yeah.
Sorry, someone remote, if you could locate it so that the rest of the audience
Sure.
can hear it.
Yeah.
Charles Reese asked, what standard body oversees QIF format? That makes sense to you?
Sure.
If you want to hold any questions and we'll answer them when we're done, I can do that.
Sure. And that particular, so what standards body oversees the QIF format? I'm going to have to get back to you on that. I have a good contact that can describe that to you in detail, and also the step AP242. There are other software for CMM and non-contact inspection. Polyworks does a great job at consuming MBD data. It'll put a plug into your CAD, extract all the information right from your CAD software, so there's no translation problems. I really like the way they do it. There is PCDMIS. They're building in a QIF importer, and so on and so forth. There are many other inspection softwares that will read in the QIF format. So here's a case study to kind of drive the point home, and why you'd want to go with model-based definition. In this case, we did a case study with this particular part here at CCAT. We cut this on our DMG Mori machine. That particular machine is a 5-axis hybrid machine. The part itself is, you can produce it 3-axis. So you can see the model there on the left. That's a SOLIDWORKS native file with, we used the DIM expert to put on the PMI. And then inside of SOLIDWORKS CAMWorks, we set up our strategies. Those are the windows that you see in the middle. Took about an hour to set up the strategies. And then what we did was, within that particular window, there's a button at the bottom left. If you click on it, it outputs that NC path that you see on the right. Similarly, we set up the inspection side. In this case, we use Renishaw's Productivity Plus software. You see the model that was imported on the left. You see the strategies that we set up via the windows within the Productivity Plus software in the middle, and then the output of the inspection program on the right. Now, what's interesting about this is that this is not a separate CMM program. This is actually an on-machine probing program, and you'll see the benefit of that here in this video. So what you're going to see here is the part actually being cut on the machine, and you're seeing pocket, that center pocket feature. Being cut there. Once that part is finished cut, the system is actually going to go through and start a probing routine. And you can see there that it's just measuring that last feature. And what it'll do is it'll output a simple inspection report. You can see down there that the width of that pocket is actually out of tolerance. And the system recognizes the tool that produced that. You can see that it has a 0 radius offset at that point. It will apply an appropriate radius offset given the deviation that it measured, and it's actually going to go back and that particular feature. Once it does that, the system will iterate and it will go through it again. In this case, we just let it go ahead and program probe everything again. We could limit it to just probe the feature that was out of tolerance, but it'll iterate and probe this again, and you can see now You can see now on the right that that feature is within tolerance, and you can see the box there up at the right. That's the feature that we're talking about. So the takeaway on this is really this slide here. If we do a comparison, we did it the traditional way, and then we did it using model-based definition. So with CAM programming, it would have taken us 2 hours. The probing program, if we did it manually, would have taken us an hour. And then because we found that we had to rework one of the features, that rework would have taken an hour. The part would have come off, we would have put it on the CMM, inspected it, and then found that we had an issue, put it back on the machine, find the coordinate system again, and then go back and recut it. Altogether 4 hours. If we use model-based definition, we're down to 40 minutes. It's not a 10-15% time savings, it's an 80% time savings. And we see this across the board. It's typically 50 to 80%. When you hear Industry 4.0 and you think, how do I get into it? What's my first step? Model-based definition is a good first step. It is an easy add-on. It is if you're going to do software updates, if you're doing yearly maintenances on your CAD or CAM software, use the IVP funding and add on the model-based definition module. It's literally with the IVP, it comes free to you, and you also pay less for your maintenance because you're getting up to $20,000 from this grant money, and the efficiencies is just it's by far, it's almost a no-brainer, a good first place to start. So the next thing that I want to talk about is intelligent production, and the next couple subjects I'm going to kind of fly through a little bit faster. Just wanted to get the point across on model-based definition and why that is such an important subject. It is the biggest bang for your buck when it comes to adopting Industry 4.0. So intelligent production, what we're talking about here is, we talked about model-based definition-driven toolpaths. We talked about model-based definition-driven measurement. But what about production? You still have variability in your production. Some parts conform, some parts are out of spec. How do you control that, and what contributes to parts being out of spec? There's a number of production sources of production variation. These are just listing a few. It starts right from your stock, so you can have deviation in the size of your stock. You can have your material can have differences in hardness. Grain orientation, if you're doing sheet metal bending, that's incredibly important when you're looking at spring back. Porosity inclusion, is it a casting? Temperature, is the stock colder, warmer? Is there some control over the temperature of the stock when you're machining it? And then bulk stress. How much bulk stress is in the material? Are you gonna, fixture it down, machine it, and you take it out of the fixture, and the bulk stresses within the part just make that part just deform out of tolerance. Those things are, if they're measurable, if they're easily measurable, it's worth measuring. And then you have machine variations. The two biggest ones here, the biggest one really is tooling. Is your tool new or is it worn? Your coolant, the type of coolant, the temperature of your coolant, the viscosity, speed overrides, and then just basically, is your machine running at the speeds and feeds that you programmed it to run, right? And then you have your technician distinctions, experience, training, preferences. If a technician starts to hear some chatter, what do they do versus somebody else? These are all variations in production. So how do we capture those variations, and how do we account for them? This is an overall picture. And what we want to do is obviously digitize as much as we can. Like I said, on your stock material, whatever you can measure, if it's size, temperature, those are easy things to measure. Hardness, those are all digital numbers, right? And then if you add an edge device, an IPC, or your controller itself has a communication protocol that you can output real-time machining data from, you can capture real-time machining data as it's happening, and your post-inspection, you have all your inspection results are digital. And what you can do with all that data, I'll kind of skip to the next slide and go back one to explain it a little bit better. This is the overall part production process, right? You have your model-based definition to start off with. You have each feature of your model-based definition, and each feature contains the all the requirements for your customer to accept that part. And then you have your stock information, whatever you can digitize there. You have your edge device connected to your production system. And then you have your operator making changes on the fly, you know, if they're allowed to. And that can be captured digitally. And then your post-inspection, which is all digital data. All of this information, it's a lot. I mean, if you think about capturing 100 data points per second, or even you can go up to 1,000 data points per second on a number of different variables as you're machining apart, you know, your spindle, the power going to your spindle, XYZ axis, if you have a trunnion table, A and C axis, you know, your current, what is the actual position from your encoder. There's just so many variables that you can extract from each of your axes. That's a lot of data. It's data that you can't easily put into like Excel and do a trend analysis. It's so much that you need the ability to make sense of that data. That's where cloud computing comes in. That's where AI comes in, and that it really can do a lot in finding a lot of information about your manufacturing processes. Essentially, what an AI system does is all this data goes up into it. There's a pre-processing, so you format the data. Everything is aligned. So for each feature, you have the tolerance ranges, then you have the signals from manufacturing, and then you have the post-inspection results. So you want to align all that data up. What the system does is it learns. So if you're using a tool, over time your tool starts to dull. How does that affect your signals? How does that affect the accuracy of your particular feature that you're making? And an AI system will output a model, and that model is a digital twin of your process. So here I'm just showing production of one part using one machine, one post-inspection machine, but it can be a collection of machines, it can be a collection of inspection systems. So your model is whatever you decided to incorporate in your production plan. And the benefits that you get out of it are this. From that model, you can start to say, hey, what if? Send it to the model and see what it outputs. So you can do, one of the obvious things out of this is status monitoring, production statistics. You know, your how well are your machine, what's your machine utilization? So you can do scheduling and all that. Predictive maintenance is a big one. This is not preventative maintenance, but predictive maintenance. Preventative maintenance would be schedule based. So you have a allotted time, say every month or every 6 months or whatever, you know, you're shutting your machine down and you're doing preventative maintenance. What you want to do is predictive maintenance, where the machine itself will start to tell you, hey, something is starting to go wrong. You better do something about it. Could be a bearing, could be something. Predictive maintenance basically almost guarantees that you'll never have an unplanned downtime. This is one of the outcomes of using an AI system. Adaptive control, that's a more advanced feature. And I'll talk more about that in the case study that I'll bring up and what that means and how that happens. Intelligent machine, just like your operator, you know, if you're adjusting speeds and feeds overrides on the fly because of what you're hearing, how the machine is behaving, that experience that you get over, you know, years and years of manufacturing, your machine is learning that. And it itself can start to tell you, hey, you better change speeds and feeds or whatever variables in your production to account for things that are kind of starting to go wrong. And then anomaly mapping. Anomaly mapping is, it really helps you to dive into what went wrong and what you can do to account for it. And I'll talk a little bit about those in detail. So here's a case study. This is as simple of a case study as you can get. One of the things that I want to say is that in order for us to use IoT technology and have an intelligent machine, we need to set up an infrastructure, right? So everything is communicating via the internet. You have to have a network in place for all this data to be streamed from the machine, you know, to your gateway, to the cloud for processing, then come back down in a model format, so then you can then do something with that model. to improve your processes. And this is kind of our 4-stage industrial IoT solutions architecture with recommended security measures all the way on the right. I'm not going to really go through this. I really just wanted to show you that at the bottom, obviously you have your analog devices. These are your machines. These are your production systems. And then what you want to either add to them, or if your machines have the ability to communicate, there's sensors that you can put on. And in the case study that I'll show you, this is what we had to do, because we did our case study on the most legacy machine that we have here at CCAT to show you that it doesn't matter if you have a old machine, you can still benefit from this technology. But adding sensors to the machine so that you give it the ability to feel and sense. And then you have your internet gateways. So these devices will communicate, will stream data to your internet gateway. Then you have your edge IoT device, which does some analytics on the actual device itself. It's basically a mini computer that can take that data in as it's coming in and pre-process it, get it ready for cloud computing. And that's what we call pre-processing. And then you're sending that data up to the cloud for, as I said, in either a logic-based, physics-based, or using AI to output a model of your manufacturing process. But this is all digital data. You're sending, it's either you can have it in your 4 walls. It's better to use cloud computing. As I said, this is a lot of data. There's cloud computing is tremendously effective at ingesting and analyzing large chunks of data very, very quickly. As an example, we analyzed, I think, an hour of cutting to produce a model using AI machine learning on premise on a very capable computer. It took about 17 hours. We took the same data, put it up to the cloud, came back in 40 minutes. It's very, very beneficial to do. But with that comes cybersecurity. This is where Concept can really help identify, what measures you need to take, but these are some of the, you can see some of the security measures. There's a lot. You want to make sure that you're protected and all that. So I just wanted to say a quick word about that. But this is the case study. So on the left, as I said, we used our Haas mini mill. It's a 2004, I believe, and it has no ability to communicate. There's no communication protocol built into it. There's no servers that you can install on it. It's a very basic 3-axis machine. So what we did was, we have some high accuracy measurement devices that we did use just to correlate. So we put you can see the Kistler systems. We used to have a rotating dyno and then a stationary at the bottom. We just wanted to get the cutting forces, but really the data that I'll show you came from the sensors you see on the right. So on the top there on the right, that's a voltage transducer. It's $50. And then a current transducer in the middle there on the right, that's another about $25, $30. And then at the bottom, that's our, if you will, our edge device. It's an Arduino with an analog to digital converter. And that's like $150. So you're talking about less than $200 here, right? And we put these sensors on each one of the motors on the machine. But particularly, all the data that I'll show is only off the spindle motor. So what we're getting with these analog devices is the power that's consumed by the motor. Okay, you can see in the middle there the Haas power supply, and I don't think you can actually, probably can't make out where the sensors are, but they're on the spindle there. So the goal here was taking the stock material that you see on the left, which started out as a 7-inch diameter cylinder, and then we wanted to machine it down to a 3-inch cylinder, going down 100 thousandths depth at a time. So you can see the machining path there in the middle. And then we use indexable inserts so we can take it off the tool and measure the tool wear under the microscope. And here's the results. So what we're looking at here, and the reason I want to show you this is to explain adaptive control. On the top left, what you're seeing is the diameter of the tool as it wore down. So we use the same inserts to cut 8 parts, and we went as aggressive as we could to really wear down that tool to show the effects. The way that we measured the tool diameter was that after we did one axial depth of cut, that spiral cut that you saw in the image, the tool went over and actually did a plunge cut into soft aluminum. And then what we did was, so every time it went down 100 thousandths, we did 400 thousandths total on per part. We had the data of the tool before it started the cut. So we had 5 different diameters. And what you're seeing on the screen there is the result of the measurement of that diameter. So we didn't use any kind of fancy measurement equipment to measure the actual cutting diameter, but we did use a microscope to see the actual tool wear, the flank wear on the tool. And so you can see from that graph at the top left, from part 2 to part 8, we were actually pretty good. The tool diameter remained pretty consistent up to part 6. And after part 6, it plummeted. And because the cutting diameter changed, now you can't see the scale, but it's altogether, it's only a 2/1000ths change in the diameter of the tool. But you can see how it affected the accuracy of the resulting feature of the cylinder. At the bottom here, that's the cylinder diameter. The cylinder, as the tool diameter decreased, the cylinder diameter increased. And similarly, as the tool wore, the cylinder height decreased. So the accuracy of the resulting feature was started to decay as my tool wore. Now, what you're seeing at the right on the top is the signal that we got from the actual manufacturing process. And the blue line, the bottom line that you're seeing, is the signal that we got, the power consumed by the spindle cutting part 2. The top line that you see is the power consumed by the spindle cutting part 8. So you can see the difference. We're looking at 1.5 kilowatts of power that the spindle motor consumes when that tool was new. So it's easier for the spindle to move that sharp edge through the material. Whereas once the tool starts to get dull, it's the spindle motor exerts more power. It needs to apply more power to move that dull tool through the material. So we're up at about 2 kilowatts by the time we get to part 8. Now, what's interesting is that it's a one-to-one, it's a linear correlation. So we can say that, okay, without even measuring my feature, just based on the signals I'm getting, I know that if my spindle motor is consuming 1.5 kilowatts, my part's going to be accurate, right? I'm going to have a plus minus deviation of less than a 5/10 thousandths. And if I know that my spindle power is starting to increase and I'm at, let's say, 1.75, I'm going to be about 1/1000ths off. And if my spindle motor is consuming 2 kilowatts of power, I know I'm going to be out 2/1000ths. So without even measuring the part, I know what the actual dimension of my part is going to be. And what I can do with that information is come up with a radius offset for my tool. So on the fly, I can say that, look, if I'm at 1.75, I'm going to apply a 1/1000ths offset for my radius. And what that's going to do is make sure that even though my tool is dull, I'm still going to get the correct diameter out. So this is, and in a simple way, this is what I mean by adaptive control, that you can use these signals to your benefit without even doing any hard measurement on the machine or on measuring the part. You can take the data and the intelligence that's there in the data, which is what the AI machine learning model spits out. This is the benefit it gives you. You always get a good part out. That's really the end takeaway of using IIoT. I won't talk much about that. I'm getting close to time.
No, I see another question.
Okay, sure. Yeah.
What are the incremental computing resources and staffing in an AI model?
So the question is, what are the incremental computing resources and staffing to implement AI models? There's a lot of systems out there, right? Microsoft Azure has their machine learning software. Amazon Web Services have their software. If you go with specifics, like for example, on our DMG Mori, that uses a Siemens Sinumeric control. So we went with a Sinumeric edge device. And then Siemens has their own cloud computing platform called MindSphere. These are pretty much, if you if you have a mechatronics engineer, electrical engineer, or even software engineer, it's on one machine, it can be a matter of a day to set it up, or it can be a matter of a week. It really depends on what machine you're putting it on. If you're putting it on, I mean, you can put sensors on a saw cutter, right? If you're using one saw to cut, you know, your raw stock, that would be an accelerometer on the system, and you can actually gather a lot of data and do predictive maintenance on that. If you have a very advanced machine like we did on our DMG machine, which is actually a hybrid, it uses both additive and subtractive, and it's a 5-axis machine, so we're talking about a lot of different motors, a lot of things that it controls. That took us a good part of a week. It took myself, and then it took 2 Siemens staff to incorporate and get the system working. So if that helps answer the question, otherwise I can get back to you and get more specifics on your particular use case and kind of give you a little bit more of a better answer. This slide here is really just showing some of the other benefits. I don't want to go into it too much, but you could see the graph at the top left. The cost savings is huge. I mean, what we're talking about is getting more good parts out of that same tool. Your scrap rate is less, you're using the tool longer, and you're getting all your parts that you're getting are good. So this has a magnified effect on your cost savings. Obviously that correlates to a reduction in scrap and all that. So that's really the takeaway from this particular slide. What I showed was us putting analog devices on a legacy machine to benefit from IIoT and an architecture that we set up here to ingest that data and come up with a process to improve the cutting cycle. And we did that to drive home the point of a supplier company coming back and say, hey, we have legacy machines, we can't benefit, our machines don't do anything. With $200 and a little bit of time, you can get systems like this working. So it can be very cost effective. There are commercial softwares out there, obviously, that do this. Here I'm just showing one of the Siemens software that runs actually on the cinematic control. This is called Analyze My Workpiece Monitor. And what it does is it does a learning process. So when you're cutting a part, it will learn. You have to give it information about the inspection. So did the part conform? Did it not conform? And what it does is over time, it comes up with this green band. So that green band is telling you your max and mins within which your signal has to reside. So you know you're going to get a good part. If your signal ever goes outside that band, it throws an anomaly. And you can set up what you want it to do once it detects an anomaly. Mostly it's just a stop. You know, it's an anomaly occurred, you stop. And the anomaly can be just before it comes outside of that band. So you can stop an error from occurring, for example, a small drill breaking, or you're doing a threading operation and you're starting to see that there's weird spikes going on from the spindle motor. Your tool is about to break, right? You can stop the process before you have that catastrophe, and you can do something about it, even if it's manual. This is an example of the what the screen looks like when it starts to throw anomalies. You can see at the graph at the bottom here, the black line is outside of that green, and up at the top there, you see that red spot, that red line that goes up. That's an anomaly spike. So this happens in real time on the cinematic control. Similarly, I think I don't have experience, but I believe I've heard that FANUC and other controllers also have these kinds of capabilities that you can add on. We're running short on time, so I'm going to speed through the next 2 subjects. Automated inspection is something that we've been talking about for a very long time, particularly non-contact inspection. You can go from hours to minutes in inspection. Here we're showing blue structured light scanning. It's a way of measuring a part without actually touching it. It uses light, structured light in this case, where you're sending out a known signal, you're getting back a deformed signal. There's a projection system or a laser that projects out a particular signal, like a single laser line or a structured light pattern. And then a camera receives that signal back. And because you're projecting it on a surface that's curved and has different geometries on it, that signal deforms. it conforms to the shape of the part. And so you're just doing signal analysis. You know what you're sending out, what you're getting back is different, and what's causing that difference is, is the shape of your part. And so you can reconstruct at very high accuracies, very high resolution, your surface. And from that, once you have that digital model, that digital twin of your physical part, then you can do whatever. You can take measurements off of that. You can use it for reverse engineering. You can use it for coming up with fixturing and holding devices and all that. Machine vision has come a long way. This is really the bulk of my background is computer vision programming and structured light development. And I'm using AI is almost a lifesaver. So where before we would have to do logic-based or physics-based programs where you say, okay, I'm looking for a visual defect on my part and then classification of that defect. So you come up with a logic structure and programming to say, well, if it's this shape, if it's this deep, you have all these requirements. You say, okay, then it's classified as this. And it's a lot of programming, and there's a lot of false detections. There's a lot of problems doing it that way, right? With the introduction of AI, now we're talking about deep learning, where you're taking pictures and you're teaching a system what's an anomaly and what's not. So what I would typically look at and say, yep, that's a dent or that's a scratch or whatever my classification method is. If I can learn it, then a computer vision using AI can learn it as well. It's fantastic. It's very impressive what these systems can do. You don't even have to be a programmer. All you have to have is a number of parts that are good and a number of parts that are bad. You take pictures of the parts that are good, and then in the software, you draw a little box around the part, and you say you classify it as good. And then if you have a bad part, you draw your box around the part, and then you draw your box around the issue, and you classify that whatever you want. And you just go through, you have a couple of hundred pictures, you classify all those pictures, and then the system learns from that. And then every time it creates a model out of that, and it uses that model. So every subsequent picture you take on parts, it'll say, okay, yeah, that's a good part, or no, that's a bad part because you have a scratch here or a dent there or whatever. So very impressive. It gets rid of all the programming, and it accounts for your environment, your lighting variability, everything. We have inference camera here at CCAT, and we'd be, one of the things I'll talk about at the end is about taking benefit of the technology we have here, so you can see how this works for your particular applications. I'm not going to go through the structural light applications. You can scan very small parts, you can scan very large parts. It's very adaptable. Generative design. This is great technology because it really, you can take advantage of additive manufacturing using generative design. So what generative design is this kind of a paradigm shift in the way you design things. Typically, you use CAD software or like a mesh modeling software to come up with a design of something, whether it's a fixture, a holding device, or a part. But the computer is typically a slave, right? You're driving it. The system, the software just gives you the tools in order to create that geometry. And you're sitting there and making decisions. The software is not doing anything other than providing that tool set so that it gives you the ability to come up with that design. Well, the paradigm shift here is that now the computer is going to help. It's going to work with you to come up with the design. So instead of the system being a slave, it now is going to be using AI and actually coming up with the design itself. All you have to do in this case is give it a few bits of information. What is your design space? So that is the volume within which you want to have your, let's say in this case, a fixture designed, right? What is the material that fixture has to be made out of? What are the loads and boundary conditions? Where is that part going to be held onto? Where are the mounting positions on it? So those can be modeled as simple cylinders, right? If I know it's going to go onto a table and I know where my hole pattern, I know I can put my cylinders here and here, and the boundary conditions there are fixed boundary conditions. And then on the area where it's going to clamp onto my part, if I'm just probing it on a CMM, my loading conditions are minimal. It's really just the weight of the part. right? Plus maybe you want to have a flat factor of safety. If you're machining it, you want to estimate your machining forces and add it in there. You can say it's a vector going in the X direction, or whatever direction vector you want to put on there, moments, all that. And then your design goals. Do you want to have this fixture be produced out of additive? Do you want it to be produced out of 5-axis machining? Do you want it to be produced out of 3-axis machining, or other manufacturing processes? And then do you want it to be as light as possible? Do you want it to be as stiff as possible? Those are the design goals. You feed all this information into this essentially black box, and you hit go. And you walk away and you come back in half an hour, 2 hours, and you have a fully designed part. And these are the kinds of things that you would see out of this kind of system. In this case, this is an example of a motorcycle bracket. The top left picture there, you see the original design, and the top right is what the generative design came up with. It was 35% reduction in weight, and in fact, it had the part actually had a stress reduction of 20%. And the part itself was produced on via additive on a Renishaw AM system. These are some other. So this is going into the manufacturing method. One of the design goals. How do you want to actually produce this? So it's not just limited to additive manufacturing, but you can see that if you specify additive, you get the biggest optimization because of the release of the considerable release of manufacturability. Additive will come up with the lightest or the most stiffest design. It'll shift material where it's not needed at all to areas where it's needed more. But you can specify die casting, you can specify 3-axis mill, you can specify 5-axis. You can see how that design slightly changes to accommodate the manufacturing that you want to use to produce that part. One of the benefits of the software that we use Paramatters here. It can do optimization of the shape plus optimization of material placement. So a lot of our additive machine, or 2 of our additive machines, can do multi-material, and some of our polymer machines can do multiple materials. So multiple materials means that you can actually get further reduction in weight, further stiffness by placing the material in strategic locations within your part, and the softwares can do that now. This is another example of if you want extreme lightweighting. The particular software that we use and some of the other more advanced software out there, they don't just do a generic structure inside, like as you would see if you were doing like a polymer print, and you can do like an infill of zigzag pattern or triangular mesh or hexagon mesh or whatever. It's not just a generic internal latticing structure. It's now using smart technology to follow the stress path. So the light weighting is true light weighting that can actually still handle the stress loads. And this is what we call mesostructure inside of generative design. I only bring this up to let you know that it exists. And this technology is going very, very far. They're getting into composite 3D weaving patterns, and non-additive type, although composite kind of falls into the additive realm, manufacturing types. So just so you know, those softwares are getting more and more advanced. So jumping into additive, you want to adopt one of these generative design softwares to really take benefit. Just some of the things I wanted to mention here. Our goal and one of the purposes of holding this this informational workshop is that we're looking for companies to go to and really we want to take on projects in the areas of IIoT, model-based definition, automated inspection, additive manufacturing. We have a lot of slots open for adoption programs. We still have money available that you can use to purchase technology. This Industry 4.0 program runs until February 2023. And if you're at all interested, it's free to you. There's no cost at all. We come on site and we'll do kind of introduction. just personal introductions. We want to learn about what your processes are, a quick walkthrough, and then what we do is we come back and the CCAT engineers kind of put our heads together and we figure out, okay, what's the first plan of attack? Where should we concentrate on? And we come back to you with recommended technology that can help improve processes. And then if you're interested, we can do demonstration. We can do introductions first if you don't know the technology, to technology providers or just ourselves. And then we could do demonstration projects, as I said before. And then if you want to adopt, we're there on site to help you implement so your folks can continue doing their day-to-day, and then also provide the funding resource to help reduce that CapEx. Some of the technology we have here to do demonstrations, we have DMG Mori laser tech. That's an additive machine. You'll see that out there once we go on. This is more for the benefit of the folks online here. The Optimec, that's a metal additive system. It can do reactive and non-reactive metals. The Renishaw AM400, the X1, we have an Ingersoll Master Print, which is a composite printer, a large robotic printer, so we can do very large ducting type parts. We've got a Stratasys, a Markforged, an E3D that has multiple tool changers on it, so we can do a variety of different materials on that one. To give you a flavor of the kinds of additive systems that we have.